Well, good morning, everybody. It's here in Calgary, Alberta. It's a crispy, cold morning, and going to warm up and going to be nice in the next couple of days, but not today. Today is pretty exciting outside if you don't bundle up. But at any rate, we'll give this just a minute or so, and we'll get going here and let everybody that is going to log in, and we'll go from there. Anyway, appreciate everybody joining today, and I hope you get something out of this. I'm sure you will, and we're going to talk about interference. We're going to this is kind of the topic that got me excited about RF some, I don't know, 35 years ago, I guess, and since then it's kind of been my passion to study interference, its effects, its causes, its solutions, its that sort of thing. And so we're going to break interference down into a number of modules that we'll look at over the next couple of months, I think, or month for sure. Next couple of months, I would think that this session, we're going to look at what interference is and what it does inside of our wireless equipment. So everybody knows the nemesis of all things wireless, right? Interference. If we all had spectrum that was clean and clear and we're able to everybody have their own channel for everything that we do, no problem at all. That's not the case. In a second here, we'll look at what a communications channel looks like, and where we'll see its components. We're going to take a short view of spectrum use and possibly how abuse has come to the fore. We're going to take a look at that a little later on in the hour. We're going to take a look at transmitter and receiver characteristics, and we're going to take a look at link budget from a little bit different view of in view of interference, and then we're going to look at three modes of interference. Next week, or next month, I should say, next edition, we'll look at the cause and effect. And I've got a third edition planned where we'll look at interference mitigation techniques that manufacturers are using today, and what we can do with the different types of equipment that we have out in the field. So anyway, let's get into this. So a universal communication channel looks something like this. People describe it in a few different ways, but ultimately, if we're initiating this communication on the left-hand side of this graphic, we have the information. In terms of wireless, we modulate that somehow. We turn the information into something that we can transmit over the air. We hand it to a transmitter. That transmitter then forwards it into our antenna device, whatever you want to call it, a duplexer, an antenna. It might be in the case of fiber, this could be fiber optics, could be all sorts of things. Anyways, so the transmitter then puts it out on the air, and over the transmission medium, which in our case happens to be free space, we send it to our receive device, which then does exactly the opposite process and takes this energy off the air, amplifies it, demodulates it, and then converts it ultimately back into the same information that we put into the system. Then when we reply, exactly the opposite happens. So maybe we initialize in this direction, we reply in that direction, conversation goes on, and our channel, this is our channel. Channel holds true for both frequency division duplex or time division duplex. These could be the same frequency divided by time, which is our normal case for broadband wireless equipment that we use for service provisioning. then our cellular network, much of it is frequency division duplex. So these days there's a different frequency for the downlink as opposed to the uplink, and so the two can coexist together on the air at the same time. Both have advantages and disadvantages, but we're not going to go into that here. All right. So once upon a time, not very long ago, actually, there was nothing radio that wasn't naturally made from the sun or from outer space or generated by the Earth itself. Until people started in the late 1800s, they started to experiment with this new thing called wireless. They used devices like spark transmitters, cat whisker receivers, that kind of thing, to be able to take and put some noise out on the air. They used Morse code to modulate this noise and send it to some distance. Marconi, who's kind of credited as the father of our modern wireless, his first long-range transmission was from Newfoundland to Ireland, and so we see it here. As time has gone on, we have gone from very, very low frequency that these spark transmitters and the early wireless devices were, and moved up in spectrum, and we've changed technology a number of times in the history of radio. So after World War I here, we moved to shortwave spectrum, and moved out of the very low frequency, moved to shortwave. A device called a Superheterodyne Receiver was developed, and so the whole idea of processing the signal at a low frequency, which is easy to do with components, and then converting it to a higher frequency to transmit over the air was developed. Then we begin the process of channelization. Receivers and transmitters could be tuned, and a number of advances, in the early 1900s that started us on our way to what we know now as radio and as wireless. So in the World War II era, we moved up again in spectrum, up into the VHF and the UHF spectrum, and radars were developed using the same radio. Their communication, voice communication for high quality for short distances was developed, and more and more wireless equipment is being put on the air. This is the key here: is that as we go down this list of time, we are going to pack the spectrum up with more and more devices, more energy, more everything. And so in the 50s and the 70s, microwave technologies developed, 50s through the 70s, I should say. And then from the 80s on here, we've moved up into millimeter wave. We've had advances like we now have devices that are capable of doing orthogonal frequency division multiplex. We have many generations now of Wi-Fi technology, and as of recent, we have multiple in, multiple out technology. We're sending multiple streams over the same channel and being able to decode them, demodulate them at the other end, and so the quantity of data that we're able to send from one end to the other of our communication channel has just exploded in the last 30 years, 20 years, that kind of thing. So this is the essence of interference, is that the more people that as demand increases, more and more people are using the spectrum that we have. And spectrum, it turns out, is not completely transparent for everything. As we go up in frequency, we shorten the range. Our free space loss increases, and so each band has its own physics. It has its own strengths and weaknesses, and so the government at some point in time here, probably shortly after World War II, as more and more demand for the spectrum came up, in order to avoid a spectral free-for-all, the government governments around the world were forced to manage the spectrum. And so they dedicated various bands to various stakeholders that were requesting it at the time. So, of course, one of the things that happens all the time is that more and more stakeholders are requesting use of the spectrum itself. So, technology drives new stakeholders. Obsolete technology, after a few years, seems to be getting in the way. So, old technology is being replaced by new technology just as fast as it can be done. So maybe the lifetime of a system in the 1960s or the late 70s, early 80s was 10 or 15 years. Now that same system, it might have a lifespan of 5 years or 3 years or 7 years or something like that, but it's getting shorter and shorter. And so data use and the internet are today's main drivers. The whole cellular world has gone in the last 20 years from circuit switched to packet switched networking. And guess what? The data is what's driving it. It's not the voice communication anymore. It's the data. The voice is a kind of an incidental thing that gets turned to data and transmitted to the other end. But nevertheless, it fosters a multitude of new stakeholders, and spectrum sharing is being forced on us in greater and greater quantities. I mean, in the US, the whole point of CBRS was to increase the use of that 3 gigahertz spectrum. And so the opportunity for interference has been steadily increasing over my career, anyways, in radio communications in whatever form that we happen to be talking about. All right. Up until the 1980s, all signal processing and transmission was analog. So we had microphones, we had amplifiers, we had filters, we had equalizers, we had all sorts of devices that were present before the modulator itself, and the information was put on the air. Since that time, since the 90s, more or less, we've gone from analog signal processing. There was a transition period to a digital signal processing, where we are processing the signal digitally that comes into our devices, whether it's analog voice that we're transmitting to the other end, or it's computer communications, whatever it happens to be. The processing of the signal is digital, but the transmission of the signal over the air is still analog. So digital signal processing that allows our modern features such as MIMO, forward error correction, data compression, sophisticated modulation schemes, and every day there's some new process that's coming along that enhances the way that we prepare the signal to be transmitted over the air. But the transmission to the other end is analog, and so it's got to be transmitted in a distortion-free manner. It's got to be received in a distortion-free manner, and then the opposite of whatever the transmission process was for the receiving process, to turn it back into the information that we put into it again. So we have this universal communications channel is still the reference model for everything that we're doing. All right. So as I started to mention here, in our communications, we have the information that we want to transmit. These days, that can be any kind of information, be it streaming, or it can be files, it can be web pages, it can be all sorts of things. It can be voice, it can be many forms. We have to take this information and then run through this modulation process here. So this modulation process has to maintain the integrity of whatever the information is that comes in, and yet prepare it for transmission over the air. So what does that mean? That means that things like synchronization pilots and all sorts of other stuff are all applied during this modulation process. And then as I'd mentioned in a previous tech talk, the blue sections here are generally digital. The green sections are analog, and of course the red section in the middle here is over the air. So in the blue section here, we are able to receive the data, store the data, process the data, change the data into a format that we want, and hang on to it for as long as we need to hang on to it. The moment that it gets handed over to the transmitter, it's now analog and we cannot store it. So whatever gets handed to the transmitter in whatever format, with whatever timing, with what, whatever the characteristics are of that signal, gets sent out over the air. So all this is important to understand in this process. One other characteristic that we have to maintain is linearity. What does that mean? That means that as we process this signal and we hand it to the transmitter has to faithfully convert that modulated signal coming into it into the energy that's going to be transmitted out of the antenna. So if I have a certain number of bits coming into the transmitter in a modulated in a certain QAM, let's say in 64 QAM or whatever it happens to be, then what's transmitted over the air has to faithfully represent that, then transmitted to the other side. I need to be able to receive that data over the air, that RF energy, and convert it back to in a reverse process to demod, and then back into the information again. And then when the other end answers, if this is a query, the other end answers, and so we have downlink this way, and we have uplink this way back to answer, or whichever direction happens to be at both sides of this channel. From my interference perspective today, looks the same. So what is interference? Let's define interference for a moment from this data model perspective. So interference is when the data out from our demodulation process does not equal the data into our modulation process. So anytime that happens, that is a form of interference. So there's a couple of things that of course that we have to, before we decide that something is interference, we have to know some things first. First of all, we have to know that all of our electronics are good, right? So we have to have ways to be able to test this, to be able to look at the statistics, look at how it's performing, find ways to test it out of our communication system, and then analyze what it's doing in the communication system to know that everything's okay. I'm not going to go into those processes in detail here. Not too important at this moment. Maybe when we get to mitigation, then how to do this is important, but not today. So we're going to assume that the equipment's all in good working order. So we got the the big check mark there. So there's three things actually that can happen to our data over the air that will cause this data out not to equal the data in process, or problem, I should say. So I can have another signal on channel, which is called co-channel, that is disturbing this receiver. So if I had another transmitter from a different communication system that was using the same frequency and the same bandwidth, or same frequency and maybe in a different bandwidth, but nevertheless we're sharing this very piece of spectrum together, then that's called co-channel interference. And it's all of this interference is going to be detected by the receiver. It's going to be decoded by the receiver. Transmitters, by their nature, are high power. So here we have high power here. we have very low power here. So we have high power here. We have, by the time it gets to our receiver, it's very low power. And so we are not so susceptible in this case to having the transmitter changed in any way by an external interference source, but we do have that process at the receiver. So anytime that we're talking about interference, what we're talking about is the receiver. We're talking about something that's happening at the receiver that is that's causing us to have our data out not equal our data in. All right. Second type of interference that we're going to talk about here in our little presentation is off-channel or adjacent channel interference. Receivers and transmitters have certain characteristics about them. We're going to get into that in a couple slides here, where some power that is near the receive frequency of my receiver here. So let's say I've got another transmitter here, and I'm hearing that other transmitter right here. Then oops, actually it should be like this. So I'm hearing the transmitter here. So I'm hearing this other transmitter here. The two signals are mixing together, and they're creating this schmozzle of signal inside the receiver, such that when it hits the demodulator can't understand or makes mistakes in understanding what it's actually hearing, and then data out does not equal data in. The third one that we're going to talk about in this series is out of band or power influence interference. So I have my little channel here. I transmit on my channel, I receive on my channel, I respond back and forth. And if I have another transmitter, very similar to the adjacent channel interference, but let's suppose it's out of band, but it's very, very close to my receive antenna. So let's say rather than hearing it at an equal level, I'm hearing it at a much higher level. So here I have my interfering transmitter. It's very near my my antenna on this end. So we'd have that situation if I back up here, right here. So let's suppose that for a moment that this is what this antenna is one system, this antenna is another system, and the antenna on the left is receiving while the antenna on the right is transmitting. That's when I have a power influence situation. Even though these might be completely different bands, and it looks by this picture, it looks like they are. The smaller antenna is a higher frequency. The longer antenna is a lower frequency, and so they're not the same at all. So it's not adjacent channel interference. But when the right hand transmitter is on the air and the left hand antenna is trying to receive, the pure power from that right hand antenna is going to take an effect the antenna on the left here that's trying to receive. So let's look at what this looks like from a spectral perspective. All right, so co-channel, we can have two different kinds of co-channel. That's really typical in our broadband wireless world, and that is that I'm receiving a communication from another system that is exactly on my frequency and exactly my bandwidth. That it would be the pure definition here of co-channel, right here. So what happens here is that the other system that's on my frequency here is going to take and raise my noise floor, my minimum signal level of my receiver that I can decode. It's going to take and raise it. So normally it would be down here, and the interference raises this level up some number of dB. So then without interference, my signal to noise ratio, let's get rid of this. Without interference, here is the received signal that I have, and so my signal to noise ratio is high. When I have this co-channel interference, then my signal to noise ratio is much less, because now instead of the noise floor being down here, my noise floor is now here. So this is the effect of that. So it desensitizes the receiver. So you think that you have a certain amount of receive sensitivity, and your signal strength is a certain amount you can take in, and you're expecting to decode a certain volume of data or have a data quality of a particular level, and co-channel can wipe that out in a hurry. The other thing that is also co-channel is this business right here. So in this situation, we're not on the same frequency, but we have overlap. So the moment that we have overlap, now this behaves in a co-channel manner. We're going to talk about interference mitigation, like I said, mentioned in not the next one, but the one after. And there are systems out there that will take and in this receiver block off this part that's being interfered with, not ignore whatever's there, and use all the rest of this for the information that it needs to deliver. However, this is new technology, relatively new. In the past, this overlap here caused the very same issue that this causes right here. Same effect, even though the two channels are not directly lined up to each other. They are close enough that we have the same raising of the noise floor, and we have and we have the same effect as that. In most modern broadband equipment have a built-in spectrum analyzer, right? Everybody's used one. And so you click on the spectrum analyzer and you do a scan, and it comes up with this waveform, and you can see the nearby transmitters that raise the signal level a lot, and then there are energy that you might see from farther away that raises it a little bit. And so the question that you have to ask yourself is, what is the effect, right? This is the issue. So we're going to take a look at what the effect is. Next session, we're going to take a look at effect, and we're going to take a look at what we can do about this. At any rate, so this is co-channel. And I would say that this is probably the most common interference. And definitely for sure in the unlicensed spectrum or the lightly licensed spectrum, this is the biggest problem. In licensed spectrum, not so much, unless somebody's made a mistake in the channel plan, or something like that's a problem. But unlicensed, this is the big issue. Oops, come on, there you go. All right. Next we have adjacent channel. Adjacent channel is a little bit different because built into receivers, because of this superheterodyne technology that I talked about that was developed after World War I, today in every single receiver, doesn't matter whether it's broadband, narrowband, whatever it is, the energy comes into the receiver at the high frequency that we're transmitting across the air. So let's say in our case with broadband equipment, it's microwave, right? It might be 3 gigahertz, it might be 2 gigahertz, it might be 5 gigahertz, and soon to be maybe 6 gigahertz. And at any rate, we've got this at a very, very high frequency comparatively. We can't process that energy at that high frequency, so right away it gets mixed down to a lower frequency so that it can be processed. So it gets demodulated, a lower frequency is delivered to the demodulator, and then out comes the processed data, and so on and so forth. In this process now, we have a device in the radio that's called a mixer. And transmitters have mixers to be able to take and bring the multipliers to bring the frequency up to the frequency over the air, because again, the frequency is generated, it's lower, and then as we as we multiply the frequency and goes through process of raising it up to the operating frequency that we need it to be, we have an opportunity at that point to provide some sort of filtering in the radio. And naturally, a broadband radio has some characteristics that we need to understand how it behaves in this environment. So let me describe the environment for a second. So at my AP site, I have 4 APs, right? They're on different frequencies. They're transmitting the same level. So it's frequency 1, 2, 3, and 4, right? When these are pointing in different directions, obviously, right? So let's say that they're north, south, east, and west. So let's just label them that: north, east, west, and south. Okay, so I've got antennas on these things. I am at a CPE location that is east of my tower. So there it is. So I am east. I'm going to receive some energy from the north, from the west, and from the south also. Or I'm going to receive some energy from a competitor or from someone else that's transmitting in the band that's not on my channel, that's somewhere else. This could be any number of scenarios that come up here. But let's look at the code at the adjacent channel that we're creating ourselves first. So we have our 4 access points. Our receiver, even though it's tuned here it's tuned to, of course, to that frequency right there, to the east frequency, F2, whatever that is. And if I tune it to F1, I do receive some signal. I see some signal. I tune it to F3, I see some signal. I tune it to the 4th frequency, I see some signal. Why is that? It's because these antennas aren't perfect. They radiate in every direction. They just radiate a little bit better in the direction that they're designed to go from the antenna's point of view. So in the direction I want to go, I might have I don't know, let's say 17 dB gain, and in the direction I don't want to go, I might have 10 or 15 or 20 or 30 dB of loss off of that 17 dB of gain. So that means I'm still radiating energy. If I'm radiating let's say 36, right, 36 dBm. In the direction that I want to go, that's my EIRP, my energy out of the antenna, the estimated isotropic radiated power is 36 dBm. If I have 20 dB of roll off in the south direction, let's say, so I'm going to receive my east signal at a particular level. So let's say it's going to be -50. I got some examples here coming up, but let's say it's going to be -50. If south is transmitting, and I've got 20 dB of isolation caused, or that's caused because of the antenna, then that same CPE location is going to receive south here at -70. Right, so this one is -50. This one is going to be -70, and so on. And we'll get to an example in just a second here. I'm getting ahead of myself. All right. So typically, this is important information right here. Typically, my desired channel has somewhere between 25 and oops, can't draw today worth a hoot either. 25 to 28 dB of protection to a signal 1 channel away. So in this case, I have built into my green receiver here, my green channel when it's tuned here, the receiver. I have 25 to 28 dB of protection here. This is 1 channel plus or minus 1 channel. This is -1 channel. This is +1 channel. And this is typically how adjacent channel interference is denoted. If I'm 2 channels away, which is the case with this guy, I have 35 to 42 dB of protection. So I need to make use of this, right? I need to know this in order to understand what I need to do as I'm working on my network, building my network, whatever the case happens to be, whatever part of the process I'm in. I need to know that in order to understand what I'm receiving right here, what's coming into that antenna, because the antenna is not frequency specific, right? The antenna that's on E here is going to receive all of this because it's all pointed at the tower. It's pointed at the orientation, the azimuth is that way. So it's going to see them all. All right. So here's an example. If green is my desired channel here, and I'm receiving the AP that I want to at -65. My signal to noise ratio should be 28 dB because my noise floor on this 40 megahertz channel, let's assume that this is going to be about -92, something like that. On the other frequencies, if I tuned this same radio to the other frequencies, I'm gonna see some level of those at that point. But if I leave it here on the green channel, the red channel is going to show up at my receiver output here into the demodulator. Wait a minute, let me get ahead of myself here again. The red channels, if I tune to the red channels, this is what I see. Let's just say that this is the energy that I see when I switch my green receiver to any one of those other three frequencies. This is one of the tests that we need to do when we suspect interference from ourselves or from something else that's on the tower site. Find the frequencies that are on the tower site and just simply tune the CPE or the radio, whatever the radio is that you're suspecting is being interfered with, and take a measurement. See what those signal levels are that you're actually able to receive off of these other sectors that are up on the tower. So down below here, I'm going to calculate what the receiver noise floor influence actually is from these red frequencies. So here I have number one is my -1 channel. This is my -1. This is my +1, and this is my +2 channel. So in this, we can see I'm receiving it at -68, but I have 28 dB of protection because it's one channel away. So my noise influence is going to be -96 dBm. Is that above the noise floor? Nope, it's below the noise floor. The thermal noise floor is higher than that. So this one is not going to bother me. If I go to my +1 channel, I'm seeing it at even a lower level. So by the time I take my 28 dB off of that signal for the protection, my actual influence here is -101, and so that is way lower than the noise floor. So in this case, I don't have any issue with those two channels, those two frequencies being received. And the third interferer here is I'm receiving it at a -70 when I tune to it. And so I'm 2 channels away, so I have 42 dB of filtering that's going on inside my receiver. So it's going to be even lower. Let me get rid of this. It's going to be even lower. So at -112. So in this case, in this scenario, I do not have any adjacent channel interference. All right, let's go to a case where we do. Okay, so example number 2. We're receiving the desired channel at a much higher signal, -42 dBm. Okay, very good. So when I tune around and I see my other 3 sectors, I have other values here that are higher. So I'm closer. I'm closer to my site in example 2 than I was at example 1. So as I get closer here, I'm going to calculate the same adjacent channel interference influence. And so on my -1 frequency, right? Again, same here, -1, +1, and +2. I'm going to see that if I take away my 28 dB, my influence is actually going to be at -73. So my noise floor was at neg 92. This influence is at neg 73. Could this cause me trouble? For sure. At the ACI influence here, neg 55, it does too. So this one can cause me trouble because it's raising my noise floor. 2 channels away here at 42, I'm receiving it at a minus 50. At 42 dB of protection, I am at neg 92. Let me clean this up. I am at neg 92. So this one is not causing me any trouble. And I have to go through this. I go through this process on any time that I have. I suspect that I have interference being caused by myself, caused by my own transmitters or my own equipment. And what might happen here? Well, what obviously in this case, I would be ill-advised to put my adjacent transmitters here in the different directions on the immediate adjacent channel. So what I should do is I should not use this channel, right? Not use it all. And I should take and go more than 2 channels away from this one. So here I got a space of 2. I probably should have so this should be probably +4, and then so I've got 1, and then +2 and +4 are my channels that I should use, or maybe -4 over here, -2 over here, I should say, would also be okay. And then I would have a guard band channel in between each of my channels, and then my noise floor is down here at neg 92 on all cases, and I'm not causing myself any interference. So this is where I can mitigate interference in my planning, is that I can know that this is going to happen and be able to do something about it. So +2 does not raise the noise floor, but +1 and -1, they certainly do raise the noise floor.
Dave, I've got a question for you.
Sure.
Another Dave is asking, but doesn't your SNR remain the same?
Does not. So the influence here, the influence of the +1 and the -1 channel in this particular example, since it raises the noise floor, my signal to noise ratio is going to be reduced by the actual effect of these carriers. And in this case, the worst carrier is going to cause the most effect. So in this particular case, my -1 here at neg 73 is going to squeeze my signal to noise ratio. So in this case, I've got at -42 to 73 is 31 dB, right? So I have 31 dB of SNR in this case. In this case, I have 50, right? So while this is the performance that I'm expecting I'm expecting that I should be able to take and run QAM 256. So I need at least 32 or a little bit more for fade margin and for my signal to noise ratio here. And if I allow these to continue operating, I'm only going to be at 31 dB as a maximum, and so I'm probably going to be stuck at QAM 64 instead of being able to achieve QAM 256. So I'm going to lose 10% of my bandwidth just simply because I've got this adjacent channel interference. Thank you for the question. So, all right. So we can see that this adjacent channel, while it's sometimes it's difficult to diagnose, we definitely, when we have an issue, we definitely need to go through the process to be able to take and know what's going on here. So how do we do this to systems that are not similar? If these were all, let's say 450 APs, let's say we're using Cambium 450s, or we're using Telrad compacts, or what Bicell's 436Qs, or whatever it happens to be. It doesn't matter what it is, as long as they're all the same. Then I can take and tune my CPE to each one of these frequencies, and I can actually get this level, right? I can actually read that level and it's going to be the exact number that my CPE is going to be experiencing, and then I can do this calculation. What about systems that are different? Well, now I use the spectrum analyzer in my CPE, and I scan the band, and since I know what my channels are, I know I can figure these 4 channels. And if I see anything else other than these 4 channels, then this is going to be interference caused by someone else that's within the band. But I should be able to take on my spectrum analyzer and pick out each one of these 4 frequencies and see the level that I'm receiving on those channels. Real important. The spectrum analyzer will then take and give you this information that you need to be able to see that that you've got a problem. So, well, co-channel here. Co-channel it has the most direct effect. Adjacent channel is subtle because it has an effect now, but it might not have an effect later on. If I have a little bit of fading going on, then my interference might go away. My interference might get worse. It's going to be variable all the time. This is why this is hard to diagnose, and I've got to take and do it from this perspective in order to make sure of what I've actually got. Boy, I wish we had a couple of hours. I could talk about this for a very long time. Anyway, so now we've got power influence. So power influence comes in a different way. Power influence interference comes from a transmitter that's on my site that's transmitting at the time that I want to be receiving. Let me say that again. Power influence is a transmitter on site, can be in band, can be out of band, that's near my receiver that is going to be influencing my noise floor while I want to receive. So he's transmitting. So this guy's transmitting, and this one is in receive mode. I have a lot of power, and I'm of course that I'm transmitting. I have a very little bit of power that I'm receiving because it's the way the nature of our link budget. So this is by far the most difficult situation to diagnose. There's a couple of clues though, and I'll talk about them before our time is up here today. All broadband receivers have a maximum adjacent channel interference rejection of about 50 dB. This is important. A receiver is not the receiver does not infinitely filter out energy that is outside of its passband. So maximum is about 50. So the response of a receiver, if I do this, so here is RSSI, and here is frequency. So my receiver is tuned here. So at 1 channel away, so let's say it's 1 channel, this is 28 dB, right? At 2 channels away, this is 42 dB. At 3 or more channels away, this is 50 dB. So my response curve of my receiver looks something like this, and it never does get to 0. So I can have, if everything is wrong about a site, I could have a 900 megahertz transmitter that's right beside a 5 gigahertz receiver, and I could be having interference issues. I could be. Not saying I would, but I could be. And so because this receiver, my receiver over here, is only providing 50 dB of protection from that transmitter, even though it's way out of the band, way out. So I've seen this situation many times where equipment just gets installed all at the top of the tower, and there's more and more equipment that's being put up there, and some of it is GPS synchronized and some of it is not, or they use different synchronization, or there's no synchronization on some and there's synchronization on others, and we end up in this situation where where at some point in time, I have transmitters on the site that are operating while I want to receive a signal from a CPE that might be some distance away. Okay. Let's remember this for a minute. Okay. So here's my example. Got our old our monopole here. I've got the green here is my system that I'm suspecting that I've got an interference on because my uplink data error rate and retransmissions from the CPE all suck. So I'm suspecting I've got a problem here. Here I've got a system that's located fairly close that is not mine. It's not synchronized with me, and so I suspect that that's the problem. So what do we do? All right. So calculating noise influence between systems is kind of difficult to get accurately, but you don't need to be real accurate in order to take and understand if there's a problem here. What you do need to know is you need to know the transmit power of all of the systems that are around you on the tower. I'm only concerned about this one, right? I'm only concerned about that one. Because when this one's in transmit, I'm suspecting that it's affecting my receiver here. So I look at the license or whatever I have to do to figure out what the transmit power of that system is, and then go get an antenna pattern, because the antenna pattern and the orientation plays a really big role in how this works. So the higher the gain of the sector, the less likely the chance is that it's going to influence an antenna beside it. The lower the gain of the sector, that meaning the wider that it is, right? If a 120-degree sector here will cause much more problems to an antenna that's beside it than what a 65 or a 45 or a 33-degree antenna will cause that same antenna parked the same distance away. So once I know this, the other thing I have to calculate or estimate is the distance between these two antennas. So then I can calculate the propagation loss between these systems. So that's in meters, right? So if or feet or whatever unit you want to take and use for that. But at any rate, that's the process. Now let me show you the example. Okay. So back from that tower site, I've got an interfering system that's at plus 43 dBm. So let's say it's a CBRS system. So it's at plus 43 dBm. The propagation loss between my two systems is, let's say, just under a meter. So at 3 gig, that works out to something less than 40 dB. So I've got 40 dB of free space loss. And then got by accident. I'll fix that later. And when I look at the two antenna patterns, I should have 30 dB of roll off from my interfering transmitter, and I've got, by my azimuth, I've got 30 dB of protection from mine. So I've got 60 dB here of isolation that the two antennas are contributing to isolate my two systems across. I know they're not GPS synced. So because I'm not synchronizing that system, so I do not know what it's doing. So I'm going to make the assumption that it can transmit when I want to receive. All right. So what's my noise floor influence? This is our the calculation here that we need to make. So our EIRP at plus 43 dBm minus 97 dB of propagation loss, right? That's 60 and 37. And I have my antenna that's here has 16 dBi gain. So let's say I'm using a 90 dB, a 90 degree sector, I should say. So it's got about 16 dBi gain, I estimate. So plus 43 minus 97, the antenna isolation contributions. I add the antenna gain of my own receiver. and then I subtract the 50 dB of adjacent channel rejection, because it's a long ways apart. It's way more than 3 channels apart in my system. And what I find out is that my answer here is that my noise floor is in fact at 88 dBm. So if I were using a 40 megahertz channel here, so it's 40, this is 40 megahertz, my noise floor is neg 92 dBm is my noise floor. And so my 88 is actually causing me 4 dB of noise floor influence, simply because it's transmitting where it is and in the direction it is and at the power level that it is. This is power influence. So I wanted to introduce that today, because next month we're going to take and use this information, and we're going to push forward from this. As exercises, I would recommend that you run these calculations on some of your sites and actually figure out what might be going on here between, do I have adjacent channel, what is my noise floor influence from my devices that are around me? Don't you know, I want to take and verify what the spectrum analyzer in my AP is actually telling me. You know, can I manually calculate what my machine is saying to me? And if I can do that, then I understand this whole business of noise and interference. That's the key. So in the next edition, I've already got the slide deck is ready to go for. We're going to talk about interference in different systems. We're going to talk about OFDM, since that is very, very popular, and we're going to talk about Wi-Fi, since that is very popular in systems like EPMP and you know, others that are based on 802.11. We're going to talk about that, and then we're going to talk about some of these mitigation techniques for co-channel, adjacent channel, and power influence interference that we've talked about this week. And as ever, if you have any questions, any feedback, want to you know, suggest another rabbit hole that we might want to go down in the next editions of Tech Talk, then please send an email to marketing@mbsiwave.com. And of course, any questions can go to marketing as well. And then Nicole, Leah, and I will all see it, and we'll answer your questions, or we'll use it as fodder for the next one of the next Tech Talks. So anyway,
Dave, I've got one question for you before you wrap.
Yes.
Susan is wondering, does the GPS spectrum experience interference?
Same way. This is, if this were, the GPS is 1536 megahertz. And this might be let's say something in the 3.6 gigahertz. If that transmitter is too close to this GPS receiver, this is what we have. Our saving grace with the GPS here is that we're not dealing with a 40 megahertz channel. We're dealing with a very narrow channel. We're dealing with a 1 megahertz or less channel that the GPS is operating on. And so the noise floor for the GPS is actually very, very low compared to the broadband noise floor. But nevertheless, this is the problem. When you have GPS interference, you got a transmitter that's nearby that's wiping out the GPS receiver in this way.
Now she's asking if Starlink satellites provide interference as well.
Nope, they're not transmit. And they would, well, and let me say that, let me take that back. They do transmit at 12 gigahertz, and that dishy antenna points them up at the sky, and so the isolation from those is going to be, you know, much more than what isolation between two sectors might be. We might be in the order of 90 or 100 dB of isolation from a dishy antenna to a panel antenna at a CPE. This would be the typical case, right? Is neighbor's got a dishy pointed up at the sky, and you've got a CPE that's on the neighbor's house that's aimed at your tower, even if it's aimed over in the direction of the dishy. There's going to be this value here of isolation. If you're aimed away from it, then you've got the CPE contributes, and the dishy contributes to that isolation. If you're aimed at the dishy, then of course it's whatever the isolation of the dishy is that you've got to calculate. And the higher the gain the antenna, the higher the isolation off azimuth is, and that's why those Starlink dishes have a motor on them to actually turn them. So they're too tight of an antenna to actually sit in one place and let the satellite go by and pick up the data from the sky and transmit back to the sky at the same time. So they actually have to follow it. So yes, it could be an issue, but less likely an issue than with our tower site, our tower situation. Whoops, this is by far the busiest environment that we have for power influence interference.
Okay, awesome. Great questions, everybody. Thank you so much. And if you have any further questions, please don't hesitate to reach out to Dave offline or email us at marketing@mbsiwave.com.
Thanks, everybody, for joining today. That's great.
Take care, Dave.
We'll talk to you later. Bye now.
Bye.